Okay, so today we'll be starting the structural analysis part of our course. So we'll be talking about trusses. So trusses in general, they're constructed of beam elements, basically, which are designed to only carry a compressive or tensile load. So typically speaking, the way we represent them, model them, is as if they're being pinned at each end. Although it might not actually look like that in real life, but it's kind of the representation we have. Because even if these connections here could carry some moment, they're not designed to carry much of a moment. Designing it such that they're not carrying a moment is the way to go. And if you're wondering why we're looking at bridges when you're a mechanical engineer, when it's a mechanical engineering course, well, you need to learn how to walk before you can run. And for you aero guys, you need to learn how to run before you can fly, I guess. The elements that make them up, we call them two-force members. Again, because the free body diagram, if we're looking at just that member, is just those two forces on either end. It is either in tension or it is in compression, and then it is connected to some sort of joint, and then those forces are transferred accordingly. So essentially, this means that there's only one thing when we're doing our analysis of the truss that we don't know about the truss. We don't know what the force is in it. It only has the one unknown. But we know what direction that force might be acting in. We just don't know its magnitude, and I guess whether or not it's positive or negative. But when we calculate the magnitude, it work out that way anyways. But we know which direction it's working in because the direction those forces are acting in need to be aligned with along the length of the beam. So here's a few typical trusses. They're often used for bridges or for roofs, so on and so forth. One example that you should be relatively familiar with. So there's some trusses you could make that would be not inherently rigid. So this structure here, if we apply force on it, essentially instead of holding the force, it'll just it'll deform and bend, and that won't be good for anyone. So we often start looking at what we call simple trusses. So simple trusses are going to be inherently rigid. You start a simple truss by just starting with a triangle, and then you add two members to the structure that are connected both to one another and to two existing joints. Then you can kind of just keep doing that until you get the size and shape that you want. So you could, I wanted to. Why is this not letting me draw instead of drag? This is okay. So we could do this. We could do this. We could do that, so on and so forth. And basically, the way the analysis works there is we break up the beams into kind of okay. So first off, we simplify the representation of the structure. So we take the actual connection there, and we just assume it's going to be a pinned connection at all of these. And then the pinned connection and down here. Typically speaking, one of these is going to be a rocker connection too. And again, that's just so it's a determinate structure. Well, not only just so it's a determinate structure, also so that when things get warm or cold, your bridge is going to shrink or expand. Well, expand when it gets warm, shrink when it gets cold, and that can cause problems if you don't have if you have a fixed connection at both ends. Then essentially your bridge might start stretching apart or crumpling or what have you. Anyhow, that's neither here nor there. We'll be talking about thermal effects next year. But anyways, yeah. So move down to simplifying our supports and our connections. Draw a free body diagram of the overall structure. That allows us to get our reactions, and then from there we can draw free body diagrams for all of the joints, and that can be used to solve the forces in the members. So essentially, if we start with just a triangle, and we know that we can that based upon that we are able to solve our equilibrium conditions based for that triangle, because the number of unknowns that we have is going to be essentially equal to the number of equations that we have. And this is what this is the beauty of the simple this is the beauty of a simple truss. Is essentially so we've got for each joint we've got one set of equations we can solve. You know, the forces on this joint in the x direction and the forces on this joint in the y direction all need to be equal to 0. And we can do that for each joint. And then when we do what we talked about here and add two members connected to one another and connected to two existing joints, essentially what we're doing is we're adding two unknowns in the form of the forces in the members itself, and we're adding two equations in the form of the forces, the x equilibrium at the new joint and the y equilibrium at the new joint. So we're able to as long as we're sticking with the simple truss, we're able to keep the situation such that we can always solve the equations that we have. And again, that's assuming that we started out with a structure that was determinate. So, which generally means that we're going to have to be having, the supports in the form of a single pin connection and a single rocker, and then work from there. So there's a couple of special loading conditions that can occur that help us simplify our analysis a fair amount. So the first of them is if we have a joint to which no external load is applied, that's important, and that joint looks like two intersecting straight lines, then the only way that you get the equilibrium to balance out is if the forces in the opposite members are equal. So, for example, if we know that the force here in AD is a tension of a certain amount, then we also know that the force here in AB is also going to be a tension, and it's also going to be the same magnitude. So that can help simplify things a fair amount, depending upon the makeup of the structure. The next one is if we have a joint to which no external load is applied. Again, that's key. There needs to be no external load at the joint. And it's got 3 members, but 2 of them are parallel. Then the force in this member is 0. Which basically is saying, we're kind of going back to this situation, except we're essentially, there's an imaginary member here, and its force is 0. So therefore, the force here needs to be 0 too. So again, I would like to emphasize again, that is not the case if there is a load applied at that joint. So we've got our force P here that's acting at that joint, then this condition doesn't apply. So we will get some force developing in member AC in this situation. And in this particular case, where the force is acting parallel to AC, then we're also getting back to this situation here, basically. So then we know that the force that does develop in AC would be equal to the load P, and it'd be in compression. But that's, that wouldn't necessarily be the case if that wouldn't necessarily be the case if we instead had a force that was acting at a different angle there. And then if we have a joint where there's no external load applied and it has 2 members attached to it, if those members are parallel, then they have equal force. And if they're not parallel, they have 0 force. Because essentially there is no way to push on this one and push on this one and have that equal to 0. Whereas you can have a joint where you have tension here, and it's equal, it balances out. In all practical situations, it also needs to be in tension. Because if you're trying to hold a compressive load like this, the instant you had any tiny little deflection or tiny little movement, then it would shift somewhat, and then they'd no longer be parallel, and then it would collapse in upon itself, and your bridge would collapse, and a lot of people would die. So don't try to do something like this to hold a compressive load. Only do that for tension. Otherwise, you are going to get sued. Now, that would be unstable equilibrium. If it starts with a compressive load, it might be stable, it might be an equilibrium position, but it's not stable because any minor deviation is going to lead to it becoming out of equilibrium. So, for example, if we have a loading situation like this, we can identify, what we can do is we can identify the 0 force members and then omit them from our analysis. So if we look at this joint C here, well, we see that we've got we've got this situation here, and it got the 2 parallel members AC and CE, and then we've got this other one here. So therefore, and there's no external load. So therefore we know that this member BC here needs to be a 0 force member. So we can omit that from our equilibrium analysis. I will say one thing here. I did talk here about how we shouldn't hold it in compression if we have only 2 members. This joint, like the span from A to C and C to E, that can still hold a compressive force. And that's just due to the fact that even though BC is a zero force member for the loading conditions shown, it would still develop enough force to prevent this angle changing from parallel. So basically, it'll have just enough to keep it in equilibrium like that. But for the purposes of like for the purposes of your static analysis, that's we're assuming that's 0. So that one can go away because of that joint here. So at B, it'll simplify your analysis because then you're only working with the 4 forces: the applied force, and then AB, BD, and BE. And then next up on this side here, so we got the joint at K, same deal as C. So we know that this member here, JK, that's a joke. It's got 0 force there too. And then once we apply that, we're saying that JK isn't holding any load. So we can basically redraw the joint at J in terms of HJ, JL, and IJ only. And then suddenly IJ here, well, that looks like a 0 force member too, because the other 2 components that are holding a load are parallel to one another, so it doesn't have anything to do to keep that joint in equilibrium. So that simplifies our analysis somewhat. And then we can go about and save ourselves a bit of time when we're trying to solve this problem. So there's another method that we can use to analyze trusses. It can be quite useful, especially if we're worried about the load in a particular member, instead of perhaps just trying to solve the load in each and every member. If we're trying to do each and every member, then oftentimes the joint method is, I mean, it's tedious, scales up with the number of elements you're working with, but it's doable. But the method of sections can be easier if you're worried about a particular member. Say, I don't know, if you had a beam that was damaged or something, and you're worried about how much load it's carrying, well, you could figure out exactly how much it is, and then compare it to, figure out how critical it is to replace it. So basically, what you do is you take your truss and you cut it up into sections, and then you treat whatever is left as a rigid body, and then you can use that to determine the forces in the members based upon the forces on that body. So basically, here we got this truss. We're slicing a line right here, and this leaves us whatever is left on this left side here. So we got this triangle here, and then we've got forces applied by the little stubs of the truss members that were cut off. So again, we just got the 2 loads, and then we got the forces from the members. Since we don't know what they are yet, by convention, unknown forces are shown to be in tension. If they do end up being in compression, and again, some of these will be in compression, because otherwise it'd be impossible for this structure to be in equilibrium. Then essentially, when you solve for it, you're just gonna end up with a negative value for the force in that member. So again, tension is positive, and is the default assumption. Compression is negative. That if you keep that in mind through the rest of your engineering career, tension is positive, compression is negative. So once we kind of break it up into this little free body diagram here, well, we got an equilibrium condition for your rigid body. that's simple enough. That was 2 weeks ago, right? So I don't know. We'll probably just take a moment about point B there, which would allow you to solve for FC here, which I think, assuming these members are equal, assuming BC and AB here are equal lengths, that would just mean that FC is going to be in compression, and its magnitude is going to be equal to P1. And then you can just continue from there, basically. The vertical components of the forces would be, well, you have to figure out what FBE is here, and then just taking the X, and then you can use the X components to figure out what the the X component. You can take the equilibrium in the X direction to figure out the FBD here. So I think so this will be in This will actually end up being in compression. This one will also end up being in compression, and then this one will be in tension. Obviously, we've been looking at 2D structures, basically. A lot of trusses are, but it doesn't need to be. So we got what we call a space truss. So the analysis is basically the same thing, just more tedious and annoying because you're working in 3 dimensions. So again, but it's still, we're still basically adding up a number of equilibriums at a point. So the point, it just, it's in 3D space, and it will have forces acting upon it in all 3 directions. But it's still just an equilibrium condition. And again, we still have the concept of a simple truss. So we start out with just a 4-pointed tetrahedron, like shown here. And essentially, as long as we start out with the reactions of the supports as determinant, which is going to require them to be some sort of combination of rollers and rockers. But as long as that's the case, then adding any additional tetrahedrons to our structure adds 3 unknowns in the forms of the forces in those 3 members. 1 unknown, 1 unknown, 1 unknown, and it adds 1 point. It adds 1 joint, and the forces, the equilibrium at that point adds another 3 equations that we can use to solve. Just the sum of the forces on that joint in the X direction, the Y direction, and the Z direction. So same idea. We're adding, if we add 3 members at a time, if we add 3 members in 1 joint at a time, then we're keeping the space truss solvable. And as for the joints themselves, so we're treating the joints as if they're a ball and socket type joint. Again, similar to how for here we treat each of the joints as if they're pin joints, regardless of kind of what they actually are. They're not designed to withstand a large amount of rotational force. So essentially, we just assume that they don't hold any, and do our analysis from there. So here's just a couple some examples of assembling and then installing in place some space trusses. So you can kind of see the connection here. Again, that you got the we got the ends of those truss members kind of going into a ball there. So this is relatively close to the assumption that it's not, it's not quite a ball and joint socket, but it's similar to it. We also got the compound trusses. So what we can do is we can essentially take two or more simple trusses and connect them together. So if we do that, as long as we again kind of keep the ratio between the number of members and the number of joints to this equation, then we're good to go. So, for example, here this one's still solvable due to the fact that essentially they didn't add too many members. If we add a redundant member here, then it becomes unsolvable, which is a problem. But kind of as long as you're keeping the connection relatively, as long as you're not trying to connect too much stuff together, then you're not going to risk making it too rigid as you go. In some cases, you might have some situations where you try to connect stuff together in a manner that would be non-rigid. So, for example, we got these two triangular-looking trusses here on the left here. If we just connect them at a point at B here, pin it together, and try to call that a day, well, then when we connect it to our supports, we got a pin here, and we got a roller here. And essentially what's going to happen is this thing's going to shoot off this way, and then this thing's going to collapse downwards. And then bridge falls, everyone dies. So we can fix that. We can add supporting members. So add a member here, CE, to kind of connect it. Or we can change the reaction at the supports. So we could have 2 pins supports here. But in general, if you take two rigid, if you take two simple trusses and kind of join them at one, join the existing structures at one spot, and just have a member in between two existing joints at another spot, then that remains solvable and rigid. So if we go back up to here, you can kind of see that's basically what they did here, and it kind of doesn't look it, but I'll show you how. So what they really did. So we had this truss here, but what they did is they went and added a triangle to that, which made that shape there the new simple truss, because we just added another triangle to our simple truss, which means that we have a new simple truss, and then we can just go and pin one of them to our other truss. So we got our other simple truss here, pin at one connection, and then add a member in between to connect it to the other one, and then it's good to go. As opposed to this one here where they did that and then added another redundant member, and everything got all screwed up as a result. So yeah, those are basically kind of the two ways you can go and jam your trusses together in order to get new solvable trusses. And that's about it for trusses. So I'll go through a few examples and a little bit about how to solve via the method of the joints and the method of sections.